Hello, seniors and senioras. This should be a very short video and assignment which contains very straightforward calculation. This most of the time, as I have mentioned, these are going to be subtraction addition, but you have to focus on the concept. Let's go over the equations we need for this. We'll need these three equations. These two and here, and some other equation we'll need. So I will go over those equations as I move along. First time, let's look into the data. What data we have? We have dose, AUC, and we have amount in the urine and volume distribution. You see, volume distribution is in liter per kilo, and there is another information here. The patient is 23 kilo. So first thing is asking for to calculate half-life. To calculate half-life, we have to use that equation. Let's see. This is the equation we have to calculate. 0.693 times V over CS. So let's do this. T half is equal to 0.693 times V by CL. So before moving along with this calculation, we have to calculate CL. How we calculate CL? For CL we have to use this equation. F dose by AUC. So now we know always F we use 1 and dose is 2 and it is milligram per kg. Milligram per kg, and AUC is 8.77, which is 8.77 milligram hour per liter. So from this we can calculate clearance 0.22805. If you look, there is a milligram per kilo, and here this would be liters. So our answer will come in liter per hour per kilo, and we know the patient weight is 70 kilo, 63 kilo. So your clearance would be 0.22805 times 63 is equal to 14.367 liter per hour. So we have now our CL. So, and if we have the volume distribution, we can directly calculate using this equation, or another option is K is equal to CL by V, which is 14.367 divided by 2.4, and this is volume distribution is per kilo, so we have to multiply with 63. This will give you K of 0.0950 per hour. and then you calculate T half. T half would be 0.693 divided by 0.0950. This is going to be 7.293 per hour, and you could have easily avoided this part. Just use that equation. For example, here 0.693 times V is what, 2.4 times 63 divided by CL. CL is 14.36 liter per hour. It would have given the same answer. So what we figured, this is your T half is your T half is 7.293 hour. Let's clean this part now. So this is a long calculation. There are lots of steps, but something you have done many times. So this would be your T half. Now what do we have to do? Now we have to calculate number 2, fraction eliminated in the urine. If you go back to the note, fraction, as I have also explained, fraction eliminated is FE. This FE is going to amount in the urine by dose, and we know that what is the amount in the urine. You see here, this would be total amount in the urine per kilo of patient. So is 0.714 divided by 2 milligram per kilo. So we do not have to make those changes because this is in milligram per kilo and this is in milligram, so we do not have to take into consideration the weight of the patient. This will give you 0.357. So your FE is, explain this, your FE is going to be 0.357. So this is your FE. I am keeping these answers because we are going to use those again. Then fraction metabolized, as I have mentioned in the class, fraction Fm is equal to 1 minus Fe. That means we have fraction Fe is going to be 1 minus 0.357 going to be 0.643. So this would be your fraction Fm is equal to is number 3, 0.357. This is fraction metabolized. Now renal clearance, CLR. What are we going to do with the CLR? If you remember, CLR, if you remember Fe, the equation is CLR, CLR divided by CL. So big one is going to be always in the bottom. So and then CLR is going to be Fe times CL. which is going to be Fe. If you remember, you know the CLR in our clearance. I think I have lost it. So our clearance was from question 1. If you have calculated, our question clearance was 239.45 milliliter per minute. So now Fe is 0.357. This is the Fe. So 0.357 times 239.45. So here we will have 85.48 milliliter per minute. So this would be our Reynolds clearance. So let's go back to Reynolds clearance. So these are the steps you have to follow in case of Reynolds clearance. So our Reynolds clearance would be 85.48 milliliter per minute. .48 milliliter per minute would be our renal clearance. Then hepatic clearance. So hepatic clearance, if you remember, hepatic clearance during the class is always CL is going to be CLH plus CLR. So now if you want to calculate CLH is equal to CL minus CLR. CL minus CLR. So CL is 239.45 milliliter per minute minus CLR is, as we have seen, this is the CLR. So here we have 85.48 is equal to 153.96 milliliter per minute. So this is our hepatic clearance. This hepatic clearance is going to be 153.96 milliliter per minute. 153.96 milliliter per minute. And then we have to calculate urinary rate constant. Urinary rate constant, I think, what are those information we have? K, and we have previously calculated K. If you remember here, and somewhere we have calculated from, for calculation of K, we need we have calculated previously K to calculate half-life. So you calculate K using the calculation of K, you use this equation. to calculate Kr. Kr is equal to, or you can also calculate K from this. So Kr is equal to K times Fe, fraction eliminated in the urine. So, and K is 0.0950 times Fe, you know, 0.357 is equal to 0.0334 per hour. So this is your Kr, and then Km we just subtract. So this would be your Kr, 0.06. Sorry, this urinary rate constant would be 0.0334, and then elimination Km is just subtract. So here Km would be, your Km is equal to K, elimination rate constant, minus Kr, and it is going to be 0.0611 per hour. So this is going to be your Km. Km is going to be 0.0611 per hour. So here let's clean this a little bit. Your Kr is 0.0334 hour. So this is our metabolic rate constant. Now if the steady state concentration of the is given every two, the average steady state concentration we are asked to calculate. If you remember that equation of average steady state concentration, C average, let's go back to that equation. C average from is F, C average F dose divided by dosing rate. Let's see, C average, where is the equation? This one. C average. So here this is the C average. For this you have to use this equation. C your C average is equal to F times dose by divided by Cl is equal to 1 and times what is pen today. So we know always we are going to use 1 for F times dose. Dose is 2 milligram per kilo per 12 hours. So this is the dosing rate. So 2 times 6.3 and tau is 12, and this 6.3 is the patient weight. This is the dose. And then we have Cl. What is the Cl we have been using? Elimination, clearance, hepatic clearance, renal clearance. The combination of these two would be, let's see, clearance is 239.57 liter per hour. and this is milligram, this is hour. So our C average is going to be, if you do this math, for some reason this not quite 23.945, then it will come, your C average would be 0.731 milligram per liter. So this would be your C average. So this is another equation, the old equation you have to use. So your C average your C average is equal to 0.731 milligram per liter. So it is writing before even I touch. Anyway. So this would be your C average. Let's play this. C average is 0.731 milligram per liter, and you know that equation you have to use for C average is equation. This is the equation that we use. See, I'm not touching, still it is writing. So this is the equation you have to use. So now once we have all those data, we have to do some more calculation. Let's mark this C average, because now this problem we have to, in this problem we have to use the previous data. So now it is asking if the same patient the clearance, in case of the same patient, clearance changed to this. We had this clearance of we had the clearance of 239.45 milliliter per minute. So as you can imagine, so in this patient, normal patient here, the patient estimate the same patient clearance has changed. So our initial clearance was 239.45 milliliter per minute, and then this patient new clearance is 49.5. So this thing you have to remember, this clearance it is also milliliter per minute. So and based on this clearance, change in clearance, we have to use those we have to calculate the rest of the parameters. So we now know that in this patient only thing has changed is clearance. Now let's do some more calculation. Fraction, so this number 8, and then total clearance. We know the total clearance, total CL is equal to CLH plus CLR. So now from the previous, from the previous part we know the CLR was 153 0.96 milliliter per minute. So then total clearance, one thing, so this is the Reynolds clearance, sorry, this is the Reynolds clearance has changed. Total clearance, so how this total clearance is going to change. So total clearance would be CL, your 153. Let's see if I'm doing everything. Yes, this was the hepatic clearance. So let's go back. I think this is the renal clearance of the patient has changed. Renal clearance, not hepatic clearance. So then what would be the total clearance? So, and CL is equal to, we know, CLH plus CLR. So our renal clearance has changed. So total clearance, we know the hepatic clearance is this one. Yes, I believe this one. So you put this 153.96 plus renal clearance. New renal clearance is 49.5. So your clearance, total clearance is going to be addition of this. That means 203.47. Here, so your total clearance is going to be 203.47 milliliter per minute. Now fraction eliminated by renal pathway, we have now total clearance. So if we know the total clearance, fraction eliminated by renal pathway, if we know this equation, Fe is equal to CLR divided by CL. So what is CLR? Our new CLR is 49.5, and the CL is, new CL is 203.45, and so Fe would be 0.243. So let's put that thing here. Fe would be 0.243. Now fraction metabolized, same thing again. Fraction metabolized, which is fraction Fm is equal to 1 minus Fe, which is going to be 1 minus 0.243 is equal to 0.757. So your fraction metabolized is this 0.757. So and then plasma half-life. To calculate plasma half-life, we have a different clearance now. We have different clearance. Let's first calculate K is CL by V. So our new CL is this one, 200. This is our new CL. So which is, new CL would be 2, our new CL is 203.47 milliliter per minute, I guess, and this, and T half we have to calculate in hours, so we have to convert this to milliliter per minute to liter per hour. So if you convert it to 203.47 times 1000 divided by 60, this will give you 12.21 hour, milliliter per hour. This is going to give you 12.21 liter per hour. So this is your K. So, sorry, this is going to be your CL, new CL is going to be 12.21 liter per hour. So in fact this is the same thing. This is in milliliter per minute. We are converting this to 12 point. This is liter per hour. Okay. So then if you know that volume distribution, you already know, which is V is equal to, so we have our CL and V is equal to 2.4 times 63, which is going to be 151 point, so 151 is going to be 151.2 liter. So we have CL and V. Now let's put this here. K is equal to CL is 12 point. Today, I don't know what's going on with the pen. It's messing up everything. K is equal to CL by V. We have our CL in liter per hour, 12.21 divided by V is 151.2 liter, and this is going to give you a new K, which is 0.0807 hour. So with that you calculate T half. So you know that T half is equal to 0.693 divided by 0.0807. This will give you a T half of 8.58 hour. So our new T half is going to be 8.58 hour. This is going to be your new T half. And then urinary rate constant. Urinary rate constant is easy. You already know that. Kr is equal to K times Fe. And we already know Fe is this. So then our Kr would be 0.0807 times 0.243. So this would be UKR. Kr is going to be K times Fe is equal to 0.0807 times 0.243, and this is going to be give you 0.0196 per hour urinary rate constant. Let's put this answer here. 0.0611 hour. This is urinary rate constant. As you know that urinary rate constant, always you have to go back to the note to do this calculation, that Kr is equal to K times Fe. The same is true for Km. And then you have to calculate metabolic rate constant. How we calculate metabolic rate constant? If you know the total K, so metabolic rate constant is going to be Km is equal to K minus Kr, and then we will have 0.0807 minus 0.0196 is equal to 0.0611 per hour. So this is your Km, 0.0611 hour. So now finally we have to calculate CSS if the same dose is given every 12 hours. to calculate CSS, steady state concentration, to calculate, that means C average you have to calculate. Again we use that equation. This is the equation. We are going to use the C average equation, but this is the equation we are going to use. So we are going to use this C average is equal to F times dose by tau divided by CL, and then although it says CSS is nothing but C average, steady state concentration, we have to calculate 1 for F, and the dose we know that 2, we know the patient weight is 63, we know that tau every 12 hour, and then clearance, total clearance is 12.21, and this C average is going to be, if you calculate, I'm sorry, this pen is messing up everything today. So it is going to be 0.8600. You see here I am not touching, but it start writing milligram per liter. So this would be your C average. It's going to be your C average is 0.8600 milligram per liter. Now if the dose in milligram required to produce the same CSS as in subjects with normal kidney function and liver function. So what would be the dose in case of the dose required, dosing rate? So first we have to determine the dosing rate. First we have to determine this one. Calculate dose by tau. So to calculate dose by tau, we have to use, so here is normal kidney and liver function, and all the data we have used previously, these are normal kidney function. Here now dose divided by tau, we have to calculate this, C average times CL divided by F. So we have to calculate dosing rate. First we have to calculate dosing rate, and dosing rate, if you know the C average of an healthy individual was, let's see, what was the C average? This was the C average for healthy person. So, and it is asking to calculate the dose required to produce the same CSS in subjects with normal kidney and liver function. So we have to use this CSS of, because here the one we have calculated CSS, this is the person with the bad kidney, because you see renal clearance has gone down a lot. So that's why you have to use and also question ask for the normal subject. So here use 7.31 times clearance of the new clearance, the disease patient, 12 point new clearance, let's say 12.21 is total clearance, and liter per hour, sorry, this is the liter per hour clearance, normal clearance. So C average is 0.731 times 12.21 hour per liter, and then F is equal to 1. So our dosing rate is 8.9255 milligram per hour. This is dosing rate. So dose by, So now it is asking for the what dose. It's not asking dosing rate. So dosing rate would be what? So it is milligram per hour. So milligram per hour, and the dosing frequency, I think it has mentioned. Yes. So average dosing state is every 12 hours. So, and also dose is given every 12 hours. So we have to, this is the dosing rate every hour. So for 12-hour dose, 8.9255 times 12 is going to be 1071 milligram would be the dose. So the dose is 107.1 milligram. So as you can see that there is a point for this exercise. You see here we have a dose of this, and with that dose, if you administer that dose to 2 milligram per kg, and that patient renal clearance has gone down. So for this reason we have to adjust the dose. So that's why the dose has gone down, because of the, you see here is 49, renal clearance is 49 and renal clearance is 85, which is half. So dose almost has been also halved. See here, in case of, that's why this question is trying, this practice or the exercise will make you understand that why dose needs to be adjusted in a renally impaired patient. This is a renally impaired patient because his renal clearance has gone down. So for this reason, so when the dose in milligram required to produce the same CSS as in subjects with normal kidney function, so in this case when clearance has gone down, average steady state concentration, C average, you see here C average CSS is 0.86, and let's go back, C average is 0.731, you see here. So that means because of the bad kidney, this CSS has gone up and gone up compared to normal persons. For this reason we have to reduce the dose, and new dose is 10.71 milligram per hour. So these are the question. You have to always be careful. I would not be able to finish that quick if I had not a cheat sheet, because I prepared those things before. I asked one of my grade students to do it for me. So here again, the point I was trying to make is this assignment will have two parts. One will be for healthy individual. This is the healthy individual, this part, and then this part would be a person which has decreased renal clearance. So one of the way to check those is CSS will go down, go up here, and your dose will go down to adjust the dose, because this is the this adjustment we have made because of the bad kidney. I hope this helps. If you have any question, but I will go over this material again on Tuesday's class a little bit. Thank you. I hope this helps. It was a long video of 44 minutes.